Find the moment of inertia of each of the following compound bodies about an axis through the point marked X perpendicular to the plane of the body. This means it's going into the page. So an example would be, if I was to draw this here, and I'm just going to draw this system. I suppose we should have a circle. Okay, if I was to draw this here, what's happening is it's going to rotate downwards, okay, and then where you're going to end up happening is it's rotating basically this way. Okay, so that's the rotation we're looking at the moment, and that's through the part X. Okay, so it's rotating this way. Okay, now find the moment of inertia of each of the following compound bodies about an axis through the point marked X perpendicular to the point of the plane. Alright, let's begin. First of all, we need to find out the rod. Alright, now the rod is being held by its end. Do you understand? It's not through the center of the rod, it's through the end of the rod. Okay, so the rod on its own, inertia of the rod on its own is 4/3 the mass of the rod L squared. Now, this formula is for length 2m, or sorry, length 2L, mass m. Does that match up with the description of the rod we have in this question? It does. The rod is of mass m and length 2L. That means its inertia is exactly the same as the formula. If it was mass 4m, we'd have to replace m with 4m, and if it was length 4L, we'd have to replace all L's with 2L's accordingly, okay? So that's the mass of the rod, okay? Now we're going to get the disc on its own. Now the disc, if you imagine, we're going to get the disc through its center, right? The moment of inertia through the disc, as if the disc was spinning around its own center, okay? So I disc, or I0 of the disc, okay, so this is the disc around its own axis, is basically what the language means there. Disc own axis is a half ml squared. Now that's the formula we proved in the first exercise. Mr squared, ml squared, same deal. Okay, so its length is L. Okay, now the problem with this is it's not rotating around O, it's rotating around X. Since both of them go into the page, they're both parallel axes. That means we can use the parallel axis theorem for the disc. Okay, so we want to find out what is the moment of the disc, the inertia of the disc around I of X. So I of X for the disc is going to be I0 plus, now do you remember what it is? It's the mass multiplied by the distance away from the axis, okay? So that's going to be plus, we call it mr squared if you want, or md squared. Now, r is defined as the distance from here to there. The distance from the center to where the distance from one axis to the other, because they're parallel to each other, but there is a distance between them. This is what we call r. Now what is r? It's 3L, isn't it? 2L going across and 1L for the radius. So it's actually 3L. Okay, so it's going to be Ix equals I0, which is a half ml squared, plus m times 3L squared. Put that in, add them together, and what you're going to get is 19/2 ml squared. Okay? Now, that's not the total inertia. We have to add the disc and the rod together. So I total is going to be I rod plus I disc. And what we'll get here is 4/3 ml squared plus 19/2 ml squared. And we'll just use our calculator for that and get 65/6 ml squared. Any questions? Just parallel axis theorem, use the correct formula. Okay, nothing there at the moment, alright? We'll go for number 2. Okay, next one is part 2. Okay, let's see what part 2 says. Part 2 is just a disc on its own with a point mass, okay? So this means this here can all disappear. Okay. Now, disk of mass m, but you notice it's going through like that, isn't it? So if I was to draw a circle, okay, let's see if we can select it. Okay, it's going around, so it's basically rotating around this axis here. So if it was to show you how it's going to rotate, it's basically rotating around like that, where it's touching x every time. If it was the same size, that is. So look, it's basically rotating around x. So it's rotating around like that, sort of like a hula hoop. Okay. So that's what's going on there. Okay. Now, the problem is it has a point mass at its end, and its usual, the formula we know where it's in its center is IO. So we're going to have to do what we usually do, okay? We're going to get I disk, so we're going to get the disk, and I0 means around its origin, right, around the circle's origin, right? So I0 is a half, it's going to be mr squared this time because r is defined as the radius. Okay. Now, what you probably haven't learned off, right, is disk around the x-axis, the disk around ix, and we're going to include the disk it's a distance r away from the x-axis, isn't it? So this is still the disk and the ix axis, so it's going to be a half. It's the parallel axis theorem because ix and I0 are parallel, so it's going to be I0 plus mr squared. That's what always is, m times the distance away. So it's going to be a half mr squared plus mr squared gives you 3/2 mr squared. Okay. Now that that's done, what's going to happen next is we now have to include the point mass. Okay. So to include the point mass, what we're going to do is the point mass is always m times its distance away from whatever axis you're talking about. We're talking about axis x, aren't we? So it's going to be m times 2r squared, which is going to give us 4mr squared. And this is the point mass. Now finally, I total, and this is I total around the x-axis, is going to be, the total inertia is going to be your disk plus your point mass, and that's going to get me 3/2 mr squared plus 4mr squared, and when you add them both together you're going to get 11mr squared over 2. It's not too bad, right? Any questions, anything you don't understand, like about the... Okay guys, the next one is, once again, we're looking for the total inertia around the y-axis. This time there's a disk of mass 2m, a rod, and there's a point mass. Now, regards to the rod is being grabbed from its end, okay? So the usual formula for the inertia of a rod from its end point and not its center is 4/3 ml squared. We have a problem this time. This is for a rod of mass m, length 2l. This time the mass is, anybody? 6m. 6m, so you're going to replace m with 6m, and the length is still 2r, so basically l gets replaced with r, so that wasn't too much of a difference, okay? So what we're going to get is 24/3, which will be 8mr squared, okay? So what did I start off with? I started off with the rod, so I'm going to start off with 8mr squared. Alright, so that's easy and done. Okay, next one. I'll start off with the disk then. I0 disk. Alright, so everything here in red is going to relay into the disk only. Okay, disk only. So I0 of the disk is a half. The formula would usually be a half mr squared. This is for mass m, length r. Okay, but in this question we can see that the mass isn't what it usually is, so it's actually going to be 2m times r squared. Alright, so the disk is going to be mr squared. Yeah. Okay. Now, this is the disk rotating about its own axis. I haven't mentioned anything about the x yet. We're going to next do the parallel axis theorem. And the parallel axis theorem states that the total inertia of the disk around the x-axis equals its inertia under the parallel axis O, plus its distance of O away from the origin. O is here. How far is O away from the origin? Huh? 3r. So it's usually md squared. That's for when the mass is m. When the mass is m and the distance is d. But in this question the mass is 2m of the disk and the distance is 3r. Okay? Now we already know what I0 is, don't we? I0 is mr squared. So put that in 19 mr squared. Yes, 19 mr squared. Okay. So that is basically everything there. Okay. Okay, so just want to make that a bit more readable. Okay, there we go, it's all up there now. Okay. Now next part is we didn't account for the point mass, did we? The point mass in the system. Okay, so now we got to do the mass. Okay. Now the point mass around the system IX. Now the usual formula is md squared. D is the distance from point mass away from the inertial axis. In this case, it's going to be a distance of 4r away. D is going to be 4. D squared is 4r squared. Its mass is still m. That will put that one up to 16 mr squared. And then I total, which is in green. This doesn't matter of adding all three parts together. The rod, which is in blue. The disc, which was in red. And now just the part we did of the point mass, or just the point mass here. And the point mass is 16 mr squared. So add all these together, what do we get? 8 plus 19 plus 16. 43 mr squared.
If you're not told the point mass, you still have to use it.
Sorry?
If you're not told that there's the point mass.
Oh no, if there's no point mass, you don't use the formula for it. It's not there.
But then, this is not mentioned. It's mentioned in part 4 and then on part 5.
Oh, it is? It's not mentioned. Oh, we're doing part 5 now.
Yeah, but why do you do point mass then in part 5? It's not mentioned in.
Oh, I've done question 4, and I've done the point mass in question 4.
Yeah.
I haven't done question 5 yet. This is all still question 4. All of this is part 4. I'm now going to do part 5 in a second. Okay, guys. Now, part 5. Okay. Now, the big problem with in the proofs we've done so far, okay? Now there's two proofs we've done so far. The first proof was the rod. And what you guys got to remember about the rod is the rod was going into the page, okay? So the rod is basically, if I can grab the rod here, rod is rotating like that. Everybody got it? Yeah. Now, the other problem is, the other one was the disc. And the disc was also rotating around an axis that's going into the page. Now the big problem with the lamina is, the lamina's proof was one that was parallel to the plane. Do you understand? So the lamina's proof doesn't include it going into the plane. Okay? I'll do it like that, yeah. So the lamina, its proof was basically on the axis. Its moment of inertia on the plane was how that was described, okay? So it's actually not rotating around like this. It's not rotating like this. If I can make it rotate like this, would be great. Yeah. It's not rotating like that. It's not, okay? It's sort of going in on itself, like
Making a cylinder.
Yeah, it's sort of making a cylinder, exactly. It's almost like making a cylinder out of itself. So it's a completely different way of rotating. Now, to fix this problem, we're going to use the perpendicular axis theorem. Now, perpendicular axis means that if I get two axes, basically, if I call this one, if I get this axis here, I might just call it two different letters, IA and IB, okay? Or I could also call it IX and IY, probably a better way of doing it. If I find out what IX is, and I find out what IY is, I can find out what IZ is by adding IX plus IY. That is the perpendicular axis theorem. Now all of a sudden, this axis I find, which is going into the page, and is perpendicular to both the X and the Y axis, this axis will be parallel to X. Therefore, we can first use the perpendicular axis theorem. Now we have two parallel axes. Then I can relate it back to the X axis. Or, sorry guys, me calling this X is mixing up, alright? So if we can just think of another letter that's not in use, P. Alright, IP and IY, okay? And the x-axis is actually parallel to our z-axis just because of the labelling involved, okay? Now, what's going to happen here is the following. Rod. The rod, we're going to start off with the rod because the rod is easy marks. I-rod. It's been kept at its end, which means 4/3 ml squared. Is it of length, not I-rod, I-laminate. I-rod, excuse me. I-rod, there is a rod there. It's length 2L. That's perfect, isn't it? It matches its formula description. If you look up your tables, it'll tell you mass M, length 2L. Matches it perfectly. Next thing we got to do is the lamina. Lamina will be done in blue here. Now, the lamina. Anybody remember the equation for our lamina? I-lamina? Anybody? We proved it in the last section. It's going to be 1/3 ml squared. And it's 1/3 ml squared for what? Mass M, length 2L. And remember I said it's completely independent of its width. It doesn't actually matter. Okay? Now that this is done, what we can say is I-lamina. So IZ is going to be, IP is 1/3 ml squared. It's the lamina of mass M. Lamina is of mass M, length 2L, so it works perfect. And then for the y-axis, it's also going to be 1/3 ml squared. Reason being, it's L both sides of the y-axis, and it's L both sides of the p-axis. So they're both 1/3 ml squared. Now using the perpendicular axis theorem, we add them together, and then we can find I-lamina. Sorry, IZ of the lamina. It's the IZ, okay, not IX. IZ of the lamina is 2/3 ml squared. We're not done with the lamina yet, because we want to find the lamina through the x-axis. Now we're going to use the parallel axis theorem. And how to use the parallel axis theorem on this one, guys? I-lamina equals IZ plus what? MD squared. Now, how far away is it from the centre? That's going to be another. So 3L mass M. So D equals 3L, M equals M. So we're going to get is 2/3 ml squared plus MD squared, which is M times 3L squared. Multiply it out. What do we get? Anybody at all? 29 over 3. Now we've got to add this to the rod, which is 4/3 ml squared. Sorry, need to write that down. I total equals lamina plus rod, which is going to be 2/3 ml squared over 3 plus 4/3 ml squared. And what do we get? 11 ml squared, or 33 over 3. Okay, next one. Number 7. difficult one. Okay. A uniform rod has a length 4L and mass m. Rod, circle, that's a square, circle, rod and circle. Okay, that's down there. Okay, Control G, Control C, paste. It's pretty handy. Quite happy about this. Now, alright, that's me setting up there, okay? Now, a uniform rod has a length of 4L and mass m. The point Q is attached to the circumference of a disc of mass m and radius L in such a way that P and Q are collinear with the overlap, with the center of the disc, and the two pieces do not overlap. They do not overlap means they only touch at one point. Okay? And P starts here, P goes to Q, and this here is mass M, isn't it? And what's its radius? L. And this here is 4L. Okay, in business there. Now, clear, do not find the moment of inertia of the system about an axis through P perpendicular to the plane of the disc. So it's the usual. It's what we've done the last time, alright? So we'll just get it done quite quickly. I of rod, okay, and this is axis P, yeah? P is at the end of the rod, yeah? It's usually it's usually 4/3 ml squared, but this time m equals m, but L equals this formula is for a length of 2L. 4L is twice as big as 2L. So 2L to be squared, yeah. So it's going to be 4/3 m 2L to be squared, which is 16/3 ml squared. Okay, so that's the first part done there, okay? Okay, and that's it there. Alright, next part. What we're going to do is we're going to look for the disc. Okay, we're going to try and sort out the disc now. Now, it's the usual with the disc, okay? Disc will be in green here. Okay, disc. We'll call the center of the circle, we'll call it C instead of O this time, right? C for the center of this disc. Now the disc, if it was spinning around its center, it would be a 1/2 ml squared. But we're not looking for it to spin around its center, we're looking for it to spin around axis P. Okay? Axis through P, perpendicular to the plane of the disc. That's what we're looking for, an axis through P. So we're going to do the parallel axis theorem. And parallel axis theorem, as we all know, is IP. This is representing the disc now. The inertia of the disc through P equals IC plus MD squared. Now, can anybody tell me what M is for this one? M equals is the mass is the circle of mass M. Yeah. So M stays as M. Is the distance, how far are we away? 5L. So distance is 5L. Okay, let's get stuck in now. IP equals a 1/2 ml squared plus MD squared, which is going to be M times 5L squared. What's IP, anybody? It's going to be 25 plus a 1/2, which is 51/2 ml squared. Okay, that's this part here. Okay, that's that part done there. Now, finally we have the disc and we have the disc and the rod. So I total, anybody? I total is disc plus rod And it's going to be 51 over 2 ml squared plus 16 over 3 ml squared. And what does that equal? Anybody? 185 over 6, yeah? Okay, perfect. Now, that's that part 1 done. Part 2. This system is free to rotate about a horizontal axis through P. Horizontal to P. Do you understand? From perpendicular to its length. Okay, perpendicular to the length of P. Its release from rest is when Q is vertically above P. Q is vertically above P. Find the angular speed when Q is vertically below P. Okay, so here's what we're going to do. I've got the total inertia of the full system. Okay, the only thing I need to remember off now is this. I only need to remember my 185 ml squared. Okay, now if you read the question carefully, what it says is that it wants them to be one above the other. Okay? Now I can draw an intermediate point for you as well if you want. Okay? Now if you imagine that it's going from all the way above, this is the starting point, it rotates down, this is the midpoint, and then it goes all the way underneath. Okay? And its moment of inertia, as we discussed, of the system is what's it described as I total. Okay, so I total inertia is 185 ml squared over 6. Now, what's going to happen here is P is here, Q is here, centre of the circle is here, and it wants to go from all the way to the top where when Q is vertically above P to when Q is vertically below P. So technically speaking, I don't need this part here. It doesn't exist in our system, okay? Now, there's a conservation of energy formula that happens when you're doing this, okay? So the conservation of energy formula is the following, okay? You have mgh, which is potential energy of your rod, plus the potential energy of your disk, okay, plus your inertial energy of your system. Now remember we said kinetic energy. We know it's not kinetic energy because it's rotating, yeah? Now usually kinetic energy is a half mv squared, okay? But rotational energy is different. It's a half IW squared. That's rotational energy, okay? So that's our rotational energy of the system, okay, at the start of the equation, right? Now, this has to equal the potential energy of the rod at the end of the equation, the potential energy of the disk at the end of the question, plus the kinetic energy, or sorry, the rotational energy of the system at the end. Okay, so this is basically one side is start, the other system is end. Now, the next thing you got to do is you got to pick a point for which the whole thing, you got to pick a point that has no potential energy. You can do it at the bottom of the circle, or you can do it through the center of the circle. To keep things simple, I'm going to go through the centre of the circle. But you guys might want to try this later on, doing it from the bottom of the circle, and make sure you get the same answer. Okay? Now, let's begin. How far is the rod above ground at this point? Rod. The rod is mg, and how far above is it? Okay? This is L. This is 4L, and up here, that's the centre of gravity of a rod, isn't it? The centre of gravity of rod, where all its weight will lie, will be the centre of the rod. That's why it's 7L. 4L plus 2L plus L, that'll give you 7L. What about the disc? Centre of gravity of a disc, dead centre. Plus another 2L plus another L. 10L? Perfect. mg 10L. Our inertia at the start of the system, if it's not moving, no inertia. 0. It has no, it has inertia, but it has no angular, because it's not moving, there's no angular. So its inertia still exists because it's still hard to turn it. It just so happens we're not turning, so therefore you have no angular energy. Okay? Now at the end of it, where's the rod located? Centre of gravity of the rod is, anybody? L plus 3L above the ground. So mg 3L. What about the disc? What about the disc? The disc has, according to our system, the disc has no height above the ground because its centre of gravity is the centre. Now if you were to draw that line further down, it would have energy and everything would make a small adjustment, but it'd still work out exactly the same way. We just do this to give us one less thing to worry about. So the disc is 0. And what about this? It's a half IW squared. Okay. IW squared therefore is equal to, a half IW squared is equal to, what's that going to be? That's 17 mgl, yeah? Minus 3 mgl gives us 14 mgl. Cross multiply both sides, cross multiply with 2. IW squared equals 28 mgl. Okay, put in your inertia. What's our inertia again? 185 over 6. Sorry guys, ml squared. W squared equals 28 mgl. Therefore, the m's will cancel. One of the l's will cancel. W squared, when we cross multiply all this out, equals 168g over 185l. W therefore equals the square root of 168g over 185l. Okay? It asks us, we reread the question, it wants to know find its angular speed. It doesn't say angular speed, that's W, okay? That's not necessarily its velocity, okay? Do you remember, W is what, guys? Angular velocity, not angular speed. So speed is how fast am I going at that point in time. And remember, speed is R omega. So it's going to be R, what's the radius length again? Can anybody tell me? What? It's going to be 5L. Okay, can anybody tell me why it's 5L? Because it's basically 2L, 2L and L. It goes 5L around. Okay? See the way this is where it's rotating around, and it's 2L, 2L and L all the way down to the bottom, the standard part, okay? So and it goes up 5L to where it was before that, so it's going this distance of 5L, okay? So the radius is 5L multiplied by the square root of 168g over 185L. Alright guys, that's it.